Please subscribe to support the channel. Imagine standing on Earth, looking up at the night sky, watching the distant points of light that represent our neighboring worlds. The question that has captivated humanity for generations isn't just whether we can reach these planets, but how long such journeys would actually take. The answer, as it turns out, is far more complex and fascinating than simply measuring distances and dividing by speed. Every journey through our solar system is a carefully choreographed dance with gravity, orbital mechanics, and the limitations of our current technology. To understand the time it takes to reach other planets, we first need to appreciate that space travel operates under rules vastly different from anything we experience on Earth. When we drive a car or fly in an airplane, we think in terms of straight lines and constant speeds. Space travel, however, is governed by orbital mechanics, where everything is always moving, and the most efficient path is rarely the shortest one. The planets aren't fixed targets waiting for us to arrive. They're moving along their own elliptical paths around the sun, each at different speeds and distances. This means that the journey time to any planet depends not just on where it is right now, but where it will be when we arrive, where Earth is when we launch, and the trajectory we choose to get there. The concept of launch windows becomes crucial in this discussion. A launch window is a specific period when the alignment of Earth and the target planet creates favorable conditions for travel. These windows open and close based on the relative positions of the celestial bodies involved, and missing a window might mean waiting months or even years for the next opportunity. This isn't just about convenience, it's about the fundamental physics of how we move through space. When we launch a spacecraft, we're not just fighting Earth's gravity, we're leveraging Earth's own motion around the sun to give us a boost. Our planet is hurtling through space at approximately 100,000 kilometers per hour, and every launch takes advantage of this cosmic carousel ride. The journey to our nearest planetary neighbor, Venus, offers an excellent starting point for understanding interplanetary travel times. Venus orbits closer to the Sun than Earth does, at an average distance of about 108 million kilometers from our star, while Earth orbits at roughly 150 million kilometers. When Venus and Earth are at their closest approach, they're separated by about 40 million kilometers. But this closest approach doesn't happen often, and even when it does, it's not necessarily the best time to launch a mission. The most efficient trajectory to Venus typically takes between 3.5 to 5 months, depending on the specific alignment and the spacecraft's capabilities. The Mariner program in the 1960s provided our first successful flyby missions to Venus, with Mariner 2 taking about 3.5 months to reach the planet in 1962. Later missions have varied in their travel times based on their specific objectives and trajectories. The Magellan spacecraft, launched in 1989 to map Venus's surface, took 15 months to reach its destination. But this longer journey time was deliberate, using a lower energy trajectory to conserve fuel and extend the spacecraft's operational lifetime once it arrived. More recent missions have demonstrated that with modern propulsion systems, the journey time hasn't changed dramatically because we're still bound by the same orbital mechanics that governed space travel decades ago. Moving outward from Venus, we come to Mars, the planet that has captured human imagination more than any other world in our solar system. Mars has been the target of more spacecraft missions than any other planet, making it a perfect case study for understanding journey times. The red planet orbits at an average distance of about 228 million kilometers from the Sun, placing it significantly farther from us than Venus. However, because Mars orbits outside Earth's path around the Sun, the geometry of travel becomes different. When Earth and Mars are at their closest approach, a configuration known as opposition that occurs approximately every 26 months, they can be as close as 55 million kilometers apart. But like Venus, this closest approach isn't necessarily when we launch missions. The most efficient path to Mars is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who calculated these trajectories in the 1920s. This elegant solution to interplanetary travel involves launching when Earth and Mars are positioned such that the spacecraft will arrive at Mars's orbit exactly when Mars itself reaches that point. It's like throwing a ball to a moving target, But that target is moving at 86,000 kilometers per hour, and you're standing on a platform that's also moving at 100,000 kilometers per hour. The Hohmann transfer to Mars typically takes between 6 and 9 months, with most missions clustering around 7 months of travel time. Every Mars mission launched by humanity has had to contend with this journey time. The Viking missions of the 1970s, the Mars Pathfinder in the 1990s, the Mars exploration rovers, Spirit and Opportunity, in the early 2000s, the Curiosity rover in 2012, and the Perseverance rover in 2020 all spent roughly 7 months traveling through space before reaching their destination. This consistency isn't coincidental. It represents the most fuel-efficient way to reach Mars with current propulsion technology. We could reach Mars faster by using more powerful rockets and burning more fuel, but the trade-offs become extreme. A faster trajectory requires exponentially more energy, which means more fuel, which means more weight, which means even more fuel to lift that weight off Earth. It becomes a vicious cycle that quickly makes missions impractical with current technology. The journey to Mars also illustrates another crucial aspect of space travel: the return trip. If astronauts were to travel to Mars, they couldn't simply turn around and come home immediately. They would need to wait for the planets to align again for a favorable return window, which means staying on Mars for approximately 13 to 16 months before the journey home. This makes a human mission to Mars a 2 to 3 year commitment, a fact that has profound implications for mission planning, life support systems, radiation exposure, and the psychological well-being of any crew making the journey. Beyond Mars lies the asteroid belt, and then we enter the realm of the gas giants, where journey times expand dramatically. Jupiter, the largest planet in our solar system, orbits at an average distance of 778 million kilometers from the Sun. This massive world, with its swirling storms and dozens of moons, has been the target of several missions, each taking a different amount of time to arrive based on their trajectories and objectives. The fastest journey to Jupiter was achieved by NASA's New Horizons spacecraft, which passed by the giant planet in just 13 months after its launch in January 2006. However, New Horizons was on a mission to Pluto and beyond, so it used Jupiter for a gravity assist, a technique that we'll explore more deeply as we continue our journey outward. Most missions to Jupiter have taken considerably longer than New Horizons. The Galileo spacecraft, which launched in October 1989, took 6 years to reach Jupiter, arriving in December 1995. This extended journey time wasn't due to slower technology. Rather, Galileo took an indirect route through the inner solar system, flying by Venus once and Earth twice to gain gravitational assists that would propel it toward Jupiter. Without these gravitational boosts, Galileo wouldn't have had enough energy to reach its destination. The Juno mission, which launched in August 2011, took 5 years to reach Jupiter, arriving in July 2016. Juno also used Earth for a gravity assist, flying by our planet in October 2013 to gain the additional velocity needed for the journey. The concept of gravity assists deserves particular attention because it fundamentally changes how we think about journey times to the outer planets. When a spacecraft flies close to a planet, it can use that planet's gravity to change its speed and direction without burning any fuel. It's like a cosmic slingshot, where the spacecraft steals a tiny amount of the planet's orbital energy. From the planet's perspective, this energy loss is infinitesimally small, but from the spacecraft's perspective, it can mean the difference between reaching the outer solar system or not. The Voyager missions, launched in 1977, used a rare alignment of the outer planets to perform multiple gravity assists, visiting Jupiter, Saturn, Uranus, and Neptune in a grand tour that would have been impossible with direct trajectories. Saturn, the jewel of the solar system, with its magnificent ring system, orbits at an average distance of 1.4 billion kilometers from the Sun. The journey time to Saturn varies even more dramatically than Jupiter, depending on the mission profile. The Pioneer 11 spacecraft, launched in April 1973, reached Saturn in September 1979, taking 6.5 years for the journey. However, Pioneer 11 had first visited Jupiter, using it for a gravity assist. The Voyager missions reached Saturn faster. Voyager 1 took 3 years and 2 months, arriving in November 1980, while Voyager 2 took 4 years, arriving in August 1981. Both had used Jupiter for gravity assists, demonstrating how the same destination can have vastly different travel times depending on the path taken. The Cassini mission to Saturn represents one of the most complex interplanetary journeys ever undertaken. Launched in October 1997, Cassini didn't arrive at Saturn until July 2004, taking nearly 7 years to complete its journey. But this wasn't a direct path. Cassini's route took it past Venus twice, then back to Earth for another gravity assist, and finally past Jupiter before reaching Saturn. This intricate trajectory was necessary because Cassini was a massive spacecraft, weighing over 5,000 kilograms and carrying the Huygens probe that would later land on Saturn's moon Titan. The direct route would have required more fuel than any rocket could reasonably carry, so mission planners choreographed this elegant celestial ballet using the gravity of multiple planets to gradually build up the speed necessary to reach Saturn. Moving even farther from the Sun, we encounter Uranus, the tilted ice giant that orbits at an average distance of 2.9 billion kilometers from our star. Only one spacecraft has ever visited Uranus, Voyager 2. Launched in August 1977, Voyager 2 reached Uranus in January 1986, taking 8.5 years to make the journey. This mission took advantage of that rare planetary alignment we mentioned earlier, using gravity assists from both Jupiter and Saturn to reach Uranus. Without these assists, the journey would have taken decades longer or might not have been possible with 1970s technology. The success of Voyager 2 at Uranus demonstrated that the outer reaches of our solar system were accessible, but it also highlighted just how long these journeys take. Neptune, the most distant of the traditional planets in our solar system, orbits at an average distance of 4.5 billion kilometers from the Sun. Like Uranus, Neptune has been visited by only one spacecraft, Voyager 2. After its encounter with Uranus, Voyager 2 continued outward, reaching Neptune in August 1989, 12 years after its initial launch from Earth. The total journey time to Neptune, even with multiple gravity assists, exceeded a decade. This single mission remains our only close-up view of Neptune, a testament to both the incredible engineering achievement of Voyager 2 and the sobering reality of how long it takes to reach the outer solar system with current technology. The journey times we've discussed so far all assume conventional chemical rocket propulsion, which has been the backbone of space exploration since the beginning of the space age. Chemical rockets work by burning fuel and oxidizer, creating high-pressure gases that shoot out of a nozzle, propelling the spacecraft forward through Newton's third law of motion. These systems are powerful and reliable, but they have fundamental limitations. The amount of energy you can extract from chemical reactions is fixed by the laws of chemistry, and the efficiency of converting that energy into motion is constrained by thermodynamics. This means that chemical rockets, no matter how well designed, can only achieve certain velocities, and those velocities translate directly into travel times. The journey to Mercury, despite being closer to the Sun than Venus, actually presents unique challenges that result in unexpectedly long travel times. Mercury orbits at an average distance of just 58 million kilometers from the Sun, making it much closer to our star than Earth's 150 million kilometers. You might think this proximity would make Mercury easier to reach, but the opposite is true. The problem is that Earth is moving very fast in its orbit, and to reach Mercury, a spacecraft must slow down significantly to fall inward toward the Sun. This requires a large amount of energy, and the trajectory must be carefully planned to match Mercury's orbital speed when the spacecraft arrives. The Mariner 10 spacecraft, which first visited Mercury in the 1970s, took nearly 5 months to reach the planet after launching in November 1973, arriving in March 1974. It used a gravity assist from Venus to help it reach Mercury's orbit. More recently, the Messenger spacecraft took an even more complex route to Mercury. Launched in August 2004, Messenger didn't enter orbit around Mercury until March 2011, taking 6.5 years to reach its destination. But this wasn't a direct journey. Messenger performed one flyby of Earth, two flybys of Venus, and three flybys of Mercury itself before finally having slowed down enough to enter orbit. Each of these flybys was carefully calculated to reduce the spacecraft's velocity relative to the Sun, allowing it to gradually spiral inward toward Mercury. This tortuous path was necessary because carrying enough fuel to slow down directly would have made the spacecraft too heavy to launch. The Bepi-Colombo mission to Mercury, launched in October 2018, is taking an even longer route, with arrival planned for December 2025, more than 7 years after launch. These mission profiles reveal a counterintuitive truth about traveling in the inner solar system. Going inward, toward the Sun, can sometimes take longer than going outward. This is because of the gravitational well created by the Sun's immense mass. Every object in the solar system is constantly falling toward the Sun, but with enough sideways velocity, it misses and ends up in orbit. To go inward, we must reduce that sideways velocity, which means fighting against the momentum we inherited from Earth. To go outward, we add to our velocity, which is easier to do. This fundamental asymmetry shapes mission planning for all inner solar system destinations. Now, having discussed the journey times with current technology, it's worth exploring what future propulsion systems might make possible. Nuclear electric propulsion, which uses a nuclear reactor to generate electricity that powers an ion drive, could reduce travel times to the outer planets significantly. Ion drives work by accelerating ions to extremely high velocities using electromagnetic fields. While the thrust produced is tiny compared to chemical rockets, ion drives can run continuously for months or years, gradually building up speed in a way that chemical rockets cannot. The Dawn spacecraft, which explored the asteroids Vesta and Ceres, used ion propulsion and demonstrated the technology's potential. For a mission to Jupiter, nuclear electric propulsion could potentially reduce travel times to as little as 2 to 3 years compared to the 5 to 6 years typical of chemical systems, though this technology is still in development for larger spacecraft. Nuclear thermal propulsion represents another promising technology. These engines heat a propellant, typically hydrogen, using a nuclear reactor and then expel it through a nozzle. Nuclear thermal rockets can achieve much higher exhaust velocities than chemical rockets, roughly twice as fast, which translates to shorter journey times and less fuel needed. NASA and other space agencies have studied nuclear thermal propulsion for decades, and recent years have seen renewed interest in developing this technology for human missions to Mars. With nuclear thermal propulsion, the journey to Mars could potentially be reduced to 3 to 4 months instead of 7, which would significantly reduce the radiation exposure and health risks for astronauts. Journey times to the outer planets could be cut roughly in half compared to current missions. The concept of continuous thrust trajectories, possible with advanced electric propulsion systems, fundamentally changes the mathematics of space travel. Instead of the Hohmann transfer orbits that dominate current mission planning, where the spacecraft coasts most of the way after an initial burn, continuous thrust allows for more direct routes. The spacecraft would accelerate for half the journey, then flip around and decelerate for the second half, arriving at the destination with minimal relative velocity. This approach could dramatically reduce travel times throughout the solar system. To Mars, such a system might reduce journey time to 2 to 3 months. To Jupiter, it could mean reaching the giant planet in a year or less. To Saturn, perhaps 2 to 3 years instead of 6 or 7 years. The challenge is that continuous thrust requires a lot of energy, more than current solar panels or chemical systems can provide, which is why nuclear power becomes essential for these advanced propulsion concepts. Solar sails represent a completely different approach to space propulsion, one that uses the pressure of sunlight itself to accelerate a spacecraft. While the force is incredibly tiny, there's no fuel required, and the acceleration never stops as long as sunlight is available. Several test missions have demonstrated solar sail technology, including Japan's Icarus probe and NASA's Light Sail projects. For a journey to Mars, a solar sail might take similar time to conventional propulsion, perhaps 8 to 12 months, but with no fuel requirements. The advantage becomes more apparent for longer missions, and especially for missions that don't require arriving quickly.
A solar sail could theoretically reach the outer planets given enough time, and proposals have been made for solar sail missions to explore the outer solar system, though journey times would be measured in decades rather than years. The most exotic propulsion concepts push the boundaries of known physics and engineering. Nuclear pulse propulsion, envisioned in Project Orion during the 1950s and 60s, would involve detonating nuclear bombs behind the spacecraft, with a massive shock absorber protecting the crew and payload. The concept was technically feasible, even with 1960s technology, and could have achieved remarkable velocities. A nuclear pulse propulsion spacecraft might reach Mars in just a few weeks, Jupiter in a few months, and even the nearest stars within a human lifetime. However, the environmental and technical challenges of detonating nuclear weapons in space have kept this technology firmly in the realm of theory. Fusion propulsion, if it becomes practical, could revolutionize space travel. Fusion reactions release far more energy per unit mass than either chemical or fission reactions, and the exhaust velocities possible with fusion rockets could exceed 100 kilometers per second compared to 4 to 5 kilometers per second for chemical rockets. With fusion propulsion, journey times throughout the solar system could be slashed dramatically. Mars might be just a few weeks away. Jupiter could be reached in a couple of months. Even Neptune, at the edge of the traditional solar system, might be accessible in less than a year. However, despite decades of research, controlled fusion power remains elusive, let alone fusion propulsion systems compact enough for spacecraft. Antimatter propulsion represents the theoretical ultimate in rocket technology. When matter and antimatter meet, they annihilate completely, converting their entire mass into energy, according to Einstein's famous equation. The energy density of antimatter is unmatched by any other fuel source. A kilogram of antimatter reacting with a kilogram of matter would release energy equivalent to millions of tons of chemical fuel. With antimatter propulsion, a spacecraft could potentially accelerate to a significant fraction of the speed of light, making not just interplanetary travel, but even interstellar travel conceivable. Journey times to any planet in the solar system would be measured in days rather than months or years. However, antimatter remains fantastically expensive to produce, difficult to store, and we can currently only create microscopic quantities. It will likely remain a theoretical technology for generations to come.
When we consider human missions versus robotic missions, travel time takes on additional significance. Robotic probes can be placed in hibernation mode during the long cruise phase of their journey, with systems powered down and only occasional check-ins from Earth. Humans, however, must be kept alive, healthy, and sane throughout the journey. This introduces numerous complications. Life support systems must recycle air and water continuously. Food must be stored or grown. Radiation shielding becomes crucial because cosmic rays and solar radiation pose serious health risks during long-duration spaceflight. The psychological challenges of spending months in a confined space with the same small crew millions of kilometers from Earth cannot be underestimated. All of these factors make journey time a critical parameter for human space exploration in ways that don't apply to robotic missions. The Mars journey time of 6 to 9 months is often cited as being at the edge of what's feasible for human crews with current technology. Astronauts on the International Space Station have demonstrated that humans can survive in space for a year or longer, but they're protected by Earth's magnetic field, which deflects much of the dangerous radiation that permeates deep space. A journey to Mars would expose astronauts to much higher radiation levels, potentially increasing their lifetime cancer risk significantly. Reducing the journey time to Mars, whether through nuclear thermal propulsion, advanced electric propulsion, or other technologies, isn't just about convenience. It's about reducing radiation exposure and making human Mars exploration more feasible and safe. For the outer planets, current journey times make human exploration effectively impossible with present technology. Even with the most optimistic assumptions about life support and radiation protection, sending humans on a 5 or 6 year journey to Saturn is beyond our current capabilities. The crew would need supplies for the entire mission, including food, water, spare parts, and fuel for the return journey. The spacecraft would need to be much larger than anything we've built for deep space, and the psychological toll of such a mission would be immense. This is why discussions of human exploration of the outer solar system inevitably involve advanced propulsion systems that could reduce journey times to a year or less. The concept of cyclar orbits offers an interesting approach to regular transportation between Earth and Mars. A cyclar is a spacecraft that follows a trajectory that regularly brings it close to both Earth and Mars, allowing it to serve as a cycling ferry between the two planets. The spacecraft would never slow down or stop. Instead, smaller shuttles would launch from each planet, rendezvous with the cyclar, transfer crew and cargo, and then return. The cyclar itself would continue on its trajectory, arriving at the other planet months later. This system could reduce the energy requirements for repeated trips to Mars because the massive cyclar spacecraft, potentially including substantial radiation shielding and life support systems, wouldn't need to accelerate or decelerate at each planet. However, the journal time on board the cyclar would still be determined by orbital mechanics, typically 6 to 7 months each way. Gravity assist trajectories, which we've touched on several times, deserve deeper exploration because they so dramatically affect journey times. The technique works because of the way velocity is relative. When a spacecraft approaches a planet, it falls into the planet's gravitational well, accelerating as it falls. If it swings around the planet and heads back out, it decelerates again, and in the planet's reference frame, it leaves with the same speed it arrived with. However, in the Sun's reference frame, the planet itself is moving, and this motion can add to or subtract from the spacecraft's velocity. A carefully planned gravity assist can change both the speed and direction of a spacecraft without using any fuel. The Voyager missions used this technique to visit all 4 outer planets, a journey that would have taken far longer and required far more fuel without the assists. The timing of gravity assists is absolutely critical. The planet must be in the right place at the right time for the geometry to work out. This is why mission planners sometimes wait years for the right planetary alignment before launching. The Cassini mission's complex route past Venus, Earth, and Jupiter wasn't arbitrary. It was the result of careful calculations to take advantage of planetary positions. Missing these windows would have meant either waiting for the next alignment or accepting a much longer journey time. For the outer planets, gravity assists are often not just helpful, but necessary, the only way to reach the destination with available technology. The specific trajectories used for each mission reveal the artistry and science of mission planning. When we send a spacecraft to another planet, we're not aiming for where the planet is now, but where it will be when we arrive. This requires solving a complex orbital mechanics problem. Given Earth's position and velocity at launch, the target planet's future position and velocity, and the spacecraft propulsion capabilities, what trajectory will successfully intercept the planet? The solution often involves sophisticated computer calculations, exploring millions of possible trajectories to find the optimal path that minimizes fuel use, travel time, or some other parameter. Sometimes the best solution isn't the fastest one. Mission planners might choose a slower trajectory if it saves fuel, allows for better arrival geometry, or provides opportunities for scientific observations along the way. Launch windows open and close based on these orbital calculations. For Mars, launch windows occur roughly every 26 months, when Earth and Mars are properly aligned. The window typically stays open for a few weeks, allowing some flexibility in launch date, but missing the window means waiting another 2 years for the next one. For the outer planets, launch windows are less frequent, and the timing is more critical, because we often need gravity assists from intermediate planets. The rare alignment that allowed the Voyager Grand Tour only occurs about once every 175 years, making those missions a unique opportunity that won't come again until the middle of the 22nd century. We should also consider what happens when missions don't go as planned. Space exploration is difficult, and not every launch succeeds. If a spacecraft misses its intended trajectory or experiences a malfunction during the cruise phase, the journey time can change dramatically. Some missions have been able to adjust their trajectories using remaining fuel reserves, but these adjustments come at a cost, either extending the journey time or reducing the fuel available for operations at the destination.
The Mars Climate Orbiter, lost in 1999 due to a navigation error, serves as a sobering reminder that reaching another planet requires precision throughout the entire journey. Every course correction must be calculated carefully, and every burn of the engines must be executed exactly as planned.
The concept of abort trajectories becomes important when considering human missions. If a crew encounters an emergency during the journey to Mars, they can't simply turn around and come home. The trajectory has already been set, and changing it requires enormous amounts of fuel. Mission planners for human Mars missions must account for free return trajectories, paths that would naturally swing the spacecraft back toward Earth if something goes wrong, or ensure the spacecraft carries enough fuel and life support for alternative routes home. These safety considerations add mass to the spacecraft and can affect the overall mission timeline, potentially extending the journey time to ensure crew safety. Communication delays also become significant for missions to distant planets. Radio signals travel at the speed of light, which seems instantaneous on Earth, but becomes very noticeable across interplanetary distances. A signal to Mars takes between 3 and 22 minutes one way, depending on the planet's relative positions. This means a round-trip communication takes between 6 and 44 minutes. For Jupiter, the light travel time ranges from about 32 to 52 minutes one way, making two-way communication take over an hour. At Neptune's distance, signals take over 4 hours to arrive, meaning any communication with a spacecraft there would require an 8-hour round-trip wait for a response. These delays don't directly affect travel time, but they do affect how missions are operated and underscore just how far apart the planets really are. The actual experience of traveling through space for months would be unlike anything most humans have encountered. On the International Space Station, astronauts can look out the window and see Earth constantly rotating below them, a reminder of home and the view that never gets old. On a journey to Mars or beyond, Earth would quickly shrink to just another bright point in the sky. The sun would remain the dominant light source, but it too would appear smaller as the spacecraft traveled outward. The stars would look the same as from Earth, their distances so vast that even our interplanetary journeys don't noticeably change their positions. The spacecraft would be a tiny bubble of life and warmth moving through an endless void. And the psychological impact of this isolation is something that future astronauts will have to manage. Time dilation, predicted by Einstein's theory of special relativity, becomes relevant only at speeds approaching the speed of light. At the velocities we currently achieve in space travel, even tens of kilometers per second, relativistic effects are negligible. For astronauts traveling to Mars, time would pass at essentially the same rate as for people on Earth. However, if we ever develop propulsion systems capable of a significant fraction of light speed, time dilation could become noticeable. At 10% of light speed, time aboard the spacecraft would pass about 0.5% slower than on Earth. Barely noticeable, but measurable with precise instruments. At 50% of light speed, time would pass about 13% slower, meaning a journey that took 1 year for the crew would correspond to about 1.15 years passing on Earth. At 90% of light speed, time dilation becomes dramatic, with time aboard the spacecraft passing less than half as fast as on Earth. However, such velocities remain purely theoretical for the foreseeable future. Considering the travel times we've discussed, it's worth putting them in perspective relative to the scale of the solar system and the cosmos beyond. Neptune, the most distant major planet, orbits at about 4.5 billion kilometers from the Sun. This seems like an enormous distance, and it is by human standards, taking 12 years for Voyager 2 to reach it. However, the nearest star after the Sun, Proxima Centauri, is about 40 trillion kilometers away, nearly 10,000 times farther than Neptune. Even traveling at Voyager speed, it would take over 70,000 years to reach Proxima Centauri. The fastest spacecraft ever built, the Parker Solar Probe, which reaches speeds of about 190 kilometers per second at its closest approach to the Sun,
would still take thousands of years to reach even the nearest star. This vast gulf between interplanetary and interstellar distances reminds us that while exploring our solar system is challenging, traveling to the stars presents obstacles of an entirely different magnitude. The dwarf planet Pluto, while no longer classified as a major planet, deserves mention in any discussion of solar system travel times. New Horizons, launched in January 2006, took 9.5 years to reach Pluto, arriving in July 2015. This was a direct trajectory with a gravity assist from Jupiter, and New Horizons was the fastest spacecraft ever sent on an interplanetary mission at launch. The journey to Pluto demonstrates the extreme distances involved in exploring even the inner edge of the Kuiper Belt, the region of icy bodies beyond Neptune's orbit. Pluto's average distance from the Sun is about 5.9 billion kilometers, though its eccentric orbit brings it as close as 4.4 billion kilometers and takes it as far as 7.4 billion kilometers. The heliosphere, the region of space dominated by the Sun's solar wind, extends far beyond the planets. Voyager 1 crossed into interstellar space beyond the heliosphere's boundary in August 2012, 35 years after its launch, and at a distance of about 18 billion kilometers from the Sun. Voyager 2 followed in November 2018, crossing the boundary at a slightly different distance. These spacecraft are still technically in our solar system, as the Sun's gravitational influence extends much farther, but they've left behind the region where the solar wind dominates. The journey to interstellar space takes decades, even for spacecraft moving at tens of kilometers per second. The Oort cloud, a theoretical spherical shell of icy objects surrounding the solar system, is thought to extend perhaps 1 to 2 light-years from the Sun, nearly halfway to the nearest star. No spacecraft will reach the Oort cloud for thousands of years, and we have no detailed plans to send a mission there. The objects in the Oort cloud are so distant and faint that we haven't directly observed them. We infer their existence from the long-period comets that occasionally fall into the inner solar system. These distances are so vast that they challenge our ability to conceive of them. The journey times we've discussed for the planets are daunting enough, measured in months and years, but the journey to the Oort cloud would span millennia. Returning to more immediate concerns, the journey times to various destinations in our solar system shape what kinds of missions are practical with current and near-future technology. Robotic missions can go anywhere we can afford to send them, given enough time. We've proven that spacecraft can function for decades in deep space, as Voyager demonstrates. Future robotic missions to the outer planets, their moons, and even the Kuiper Belt beyond are feasible, limited mainly by budget and scientific priorities rather than fundamental technical barriers. These missions will continue to have long journey times, but for robots, time is less of a constraint.
Human missions face much stricter limits. Mars is at the edge of what's possible with current technology, requiring roughly 2 to 3 years for a complete mission, including the stay on the surface. Reducing this time would open up possibilities and reduce risks, making Mars missions more attractive. Missions to the asteroids between Mars and Jupiter could have similar or shorter journey times, depending on which asteroid is targeted. Some near-Earth asteroids can be reached in just a few months. However, missions to Jupiter's moons or Saturn's moon Titan, which have been proposed as destinations for human exploration due to their potential for harboring life, would require breakthroughs in propulsion technology to make the journey times acceptable. The moons of the outer planets deserve special mention as destinations because several of them are among the most scientifically interesting places in the solar system. Jupiter's moon Europa is thought to have a liquid water ocean beneath its icy crust, making it a prime target in the search for extraterrestrial life. Saturn's moon Enceladus also appears to have a subsurface ocean and even jets of water vapor erupting from its south polar region. Titan, Saturn's largest moon, has a thick atmosphere and lakes of liquid methane and ethane on its surface, making it the only other place in the solar system besides Earth with stable surface liquids. Journey times to these moons are determined by journey times to their parent planets, plus some additional time for orbital insertion and maneuvering. Missions to these moons typically arrive at the planet first, then spend months or years maneuvering into position to study the moons in detail.
Seasonal changes on the planets can affect mission planning and journey times in subtle ways. Mars has seasons similar to Earth because its rotation axis is tilted at about 25 degrees, close to Earth's 23.5 degrees. Mission planners must consider what season it will be on Mars when the spacecraft arrives, as this affects landing site selection, dust storm probability, and solar panel efficiency. The giant planets also have seasons, though they're much longer due to the planet's longer orbital periods. Saturn seasons last about 7 Earth years each, and the angle of sunlight on the rings changes dramatically over a Saturnian year. Mission planners for Cassini had to consider these factors when planning the mission timeline and deciding how long the spacecraft would remain operational to observe different seasonal conditions. The environmental conditions during the journey affect spacecraft design and reliability. In the inner solar system, near the Sun, solar radiation and heat are the primary concerns. Spacecraft bound for Mercury must be designed to withstand intense sunlight and heat, with special thermal protection systems. In the outer solar system, cold becomes the challenge. Jupiter receives only 4% as much sunlight per square meter as Earth, and Neptune receives only about 1/10 of 1%. At these distances, solar panels become inefficient, which is why missions to the outer planets typically use radioisotope thermoelectric generators, nuclear batteries that produce electricity from the heat of radioactive decay. These power sources provide steady, reliable power throughout the long journey and subsequent mission operations. Dust and micrometeoroids pose another hazard during long interplanetary journeys. While space is mostly empty, it's not completely empty. Tiny particles, some no larger than grains of sand, move at high speeds and can damage spacecraft if they hit. The longer the journey, the greater the cumulative chance of such impacts. Spacecraft are designed with some redundancy to tolerate minor damage, and critical systems may be shielded, but there's always risk. The asteroid belt, despite its reputation, is not particularly dangerous. The asteroids are spread over such a vast volume that the chances of hitting one are negligible. The real concern is the fine dust that pervades the solar system, invisible but ever present. Looking toward future exploration, several missions are currently in development or have been proposed that will test new technologies and push the boundaries of travel times. NASA's Artemis program aims to return humans to the moon and establish a sustainable presence there, serving as a testing ground for technologies and procedures that could later enable Mars exploration. The Gateway, a planned space station in lunar orbit, would serve as a staging point for lunar surface missions, and potentially as a departure point for Mars missions. While the moon is only a few days away, much closer than any planet, the experience gained there will be invaluable for longer journeys. Various space agencies and private companies have entered the arena of interplanetary travel planning. SpaceX has announced ambitious goals for Mars colonization, proposing to develop the Starship system capable of carrying large numbers of passengers and significant cargo to Mars. The company's vision involves reducing the cost of Mars travel through reusability and mass production of spacecraft, potentially enabling journeys for hundreds or even thousands of people. However, even with the most optimistic projections for Starship's capabilities, the journey time to Mars would still be governed by orbital mechanics, likely remaining in the 6 to 9 month range unless breakthrough propulsion technologies are developed. What could change is the frequency of missions, with launch opportunities potentially utilizing every 26-month window rather than occasional missions years apart. The concept of in-space refueling could significantly impact journey times and mission capabilities. Current mission designs must carry all the fuel needed for the entire journey from Earth's surface, which severely limits what's possible. If spacecraft could refuel at orbiting depots, whether around Earth, the Moon, or even Mars, they could potentially use more fuel-intensive but faster trajectories. A spacecraft might burn more fuel to shorten the journey time, knowing it can refuel at the destination. This approach could reduce Mars journey times to the lower end of the current range, or potentially even shorter. Fuel depots would need to be supplied, either from Earth or by mining water ice from the Moon or asteroids and converting it into rocket propellant through electrolysis. These infrastructure developments are years or decades away, but could transform how we think about interplanetary travel. Aerobraking represents another technique that affects mission timelines, particularly for arrival at planets with atmospheres. When a spacecraft reaches Mars, Venus, or any planet with an atmosphere, it can use that atmosphere to slow down instead of burning fuel. The spacecraft dips into the upper atmosphere on each orbit, and the atmospheric friction gradually reduces its velocity, allowing it to settle into a lower orbit over weeks or months. This technique was used by Mars Global Surveyor, Mars Odyssey, Mars Reconnaissance Orbiter, and many other missions. While aerobraking doesn't affect the interplanetary cruise time, it does add weeks or months to the overall mission timeline before science operations can begin. However, the fuel savings are so substantial that mission planners accept this additional time. Without aerobraking, spacecraft would need to carry much more fuel for orbital insertion, making them heavier and more expensive to launch. The psychological aspects of long journey times deserve deeper consideration, especially as we contemplate sending humans on missions lasting months or years. Studies of isolated environments on Earth, such as Antarctic research stations, submarines, and simulation habitats, provide some insights into what astronauts might experience. However, these analogs are imperfect because even the most isolated Antarctic station can be evacuated in an emergency, and submarines eventually return to port. A spacecraft bound for Mars reaches a point of no return, where turning back becomes impossible, because it would take just as long or longer than continuing forward. The crew must live with the knowledge that they're committed to a multi-year journey with no possibility of early return, no matter what happens. Communication delays exacerbate the isolation. On the International Space Station, astronauts can have real-time conversations with mission control and their families. On a journey to Mars, each exchange of messages involves delays of several minutes, making real conversation impossible. Messages must be recorded and sent, then the sender must wait minutes for a response. This asynchronous communication continues throughout the mission, with the delay growing as the spacecraft travels farther from Earth and then shrinking again on the return journey. For missions to the outer planets, if humans ever venture there, communication delays of hours would make Earth seem incredibly distant. The crew would be truly on their own, making decisions without the immediate support of mission control.
The medical challenges of long-duration spaceflight remain one of the key obstacles to human exploration beyond Mars. Microgravity causes bone density loss and muscle atrophy, effects that continue throughout the journey. Astronauts on the International Space Station exercise for 2 hours daily to combat these effects, but they still experience significant physiological changes during missions lasting 6 months or more. On a journey to Mars, astronauts would spend 6 to 9 months in microgravity traveling there, then potentially over a year on Mars at 1/3 Earth's gravity, then another 6 to 9 months in microgravity on the return trip. The cumulative effects on their bodies would be substantial. Artificial gravity through rotating spacecraft has been proposed as a solution, but building and operating such systems adds complexity and mass to the mission. Radiation exposure during the journey represents perhaps the most serious health risk. Earth's magnetic field protects us from most cosmic radiation, and the atmosphere provides additional shielding. In deep space, there is no such protection. Galactic cosmic rays, high-energy particles from distant supernovae and other sources constantly bombard spacecraft. Solar particle events, eruptions from the sun that send bursts of radiation through the solar system, pose additional risks. The longer the journey, the greater the cumulative radiation exposure. Current spacecraft designs include some radiation shielding, typically water or polyethylene, but adding enough shielding to reduce radiation to safe levels would make spacecraft prohibitively heavy. This is why reducing journey times through faster propulsion systems isn't just a matter of convenience, but potentially a matter of crew survival. The concept of hibernation or suspended animation has been explored as a potential solution to the challenges of long-duration spaceflight. If astronauts could be placed in a state of reduced metabolism for the journey, they would age less, require less food and water, produce less waste, and potentially suffer less psychological stress from confinement and isolation. Some animals naturally hibernate, and medical procedures like therapeutic hypothermia demonstrate that human metabolism can be temporarily slowed. However, hibernating humans for months while in microgravity, then waking them safely at the destination, remains firmly in the realm of science fiction for now. The medical challenges are immense, and we're far from having the technology to implement such systems. If successful, though, hibernation wouldn't reduce the actual journey time, but would make long journeys much more tolerable for crews. The selection and training of crews for long-duration missions involves considerations that go beyond technical skills.
The crew must be able to work together effectively in a confined space for years, managing stress, resolving conflicts, and maintaining morale despite isolation and danger. Psychological screening, team building, and preparation for the mental challenges of the journey are as important as technical training. Some space agencies have conducted simulation missions, such as Mars 500, where crews lived in isolation in a mock spacecraft for 17 months, the approximate duration of a Mars mission. These simulations revealed psychological challenges and helped identify strategies for maintaining crew well-being during long missions. The logistics of supporting humans during months-long journeys are daunting. A crew of 6 on a 9-month journey to Mars would need substantial quantities of food, water, and oxygen. While water and oxygen can be partially recycled using life support systems, some loss is inevitable and reserves must be carried. Food must be stored for the entire journey, as growing significant amounts of food in space remains impractical with current technology. The waste produced must be stored or processed. Every kilogram of supplies must be launched from Earth at enormous cost, so efficiency is paramount. This is why reducing journey times through faster propulsion systems isn't just a matter of convenience, but potentially a matter of crew survival. The asteroid belt, while not particularly dangerous as we discussed earlier, does offer potential destinations that could be reached in timeframes similar to or shorter than Mars missions. Some asteroids have orbits that bring them relatively close to Earth, and missions to these near-Earth asteroids could serve as stepping stones to deeper space exploration. The OSIRIS-REx mission, which visited asteroid Bennu and returned samples to Earth, took about 2 years to reach its target and spent another 2 years studying the asteroid before beginning the return journey. The Dawn mission, which orbited both Vesta and Ceres in the asteroid belt, took about 4 years to reach Vesta, then another 1.5 years to travel from Vesta to Ceres. These missions demonstrate that asteroids, at least some of them, are accessible with current technology and reasonable journey times. Mining asteroids for resources has been proposed as a way to support space exploration and even provide economic benefits to Earth. Some asteroids are thought to contain valuable metals in concentrations far exceeding Earth's richest ore deposits. Water ice, believed to exist on some asteroids, could be processed into rocket fuel, providing a source of propellant in space. The journey times to asteroids vary enormously depending on which asteroid is targeted. Near-Earth asteroids might be reached in months, while main-belt asteroids typically require years. The economic viability of asteroid mining depends partly on these journey times. Shorter journeys mean faster returns on investment and reduced mission costs. The moons of Mars, Phobos and Deimos, represent interesting intermediate destinations. These small, irregularly shaped moons orbit close to Mars, and a mission to them would have essentially the same journey time as a mission to Mars, 6 to 9 months. However, landing on Phobos or Deimos would be much easier than landing on Mars due to their extremely weak gravity. A mission to the Martian moons has been proposed as a possible precursor to landing on Mars itself, allowing astronauts to study Mars from orbit and its moons while deferring the challenges of landing and launching from Mars's surface. The Martian Moons Exploration Mission, being developed by Japan, plans to visit both moons and return samples, demonstrating that these bodies are accessible targets for exploration. Jupiter's 4 large moons discovered by Galileo and known as the Galilean satellites each present unique characteristics and challenges. Io is the most volcanically active body in the solar system, with sulfur and silicate volcanoes constantly resurfacing the moon. Europa, as mentioned earlier, likely harbors a subsurface ocean that could potentially support life. Ganymede is the largest moon in the solar system, bigger than the planet Mercury, and has its own magnetic field. Callisto is heavily cratered and geologically inactive. The journey time to these moons is determined by the journey to Jupiter itself, typically 5 to 6 years with current technology, though New Horizons demonstrated that 13 months is possible if the mission doesn't need to slow down for orbital insertion. The Europa Clipper mission, scheduled for launch in the coming years, will take about 5.5 years to reach Jupiter using gravity assists from Mars and Earth. Once there, it will perform dozens of flybys of Europa, studying the moon's ice shell and the ocean beneath. The journey time for Europa Clipper is typical for missions to the Jupiter system, and any future mission, whether robotic or human, to Europa's ocean would face similar travel times unless new propulsion systems are developed. The scientific importance of Europa and the tantalizing possibility of finding life there make these long journey times acceptable for robotic missions, but they present severe challenges for human exploration.
Saturn's moon Titan stands as one of the most intriguing destinations in the solar system. Its thick atmosphere, composed primarily of nitrogen with methane and other hydrocarbons, is denser than Earth's atmosphere. The surface temperature is around minus 180 degrees Celsius, cold enough that methane exists as a liquid, forming rivers, lakes, and seas. Organic chemistry in Titan's atmosphere and on its surface may resemble the chemistry that preceded life on Earth. The Cassini mission discovered all these wonders during its 13 years orbiting Saturn, and the Huygens probe successfully landed on Titan in 2005, transmitting data from the surface for about 90 minutes. The journey time to Titan is essentially the same as to Saturn, 6 to 7 years for a typical mission, though as Cassini demonstrated, complex trajectories with multiple gravity assists can extend this to 10 years or more. The Dragonfly mission, selected by NASA and scheduled to launch in 2027, will be a rotorcraft lander that will fly to dozens of locations on Titan's surface, studying its chemistry and searching for signs of life. Dragonfly will take about 7 years to reach Titan after launch, arriving in 2034. This mission exemplifies how even with modern technology and careful planning, reaching the outer solar system requires patience. The flight time represents years of waiting between launch and arrival, years during which the spacecraft travels through the void, its course set, its systems periodically checked, but otherwise inactive, coasting towards its distant destination.
Enceladus, another moon of Saturn, has become a high-priority target for astrobiology. The Cassini mission discovered that Enceladus shoots jets of water vapor and ice particles from fractures near its south pole, material that comes from a subsurface ocean. The ocean is in contact with a rocky core, which could provide chemical energy for life. The jets shoot material into space, where it can be sampled by spacecraft without even needing to land. This makes Enceladus an attractive target despite the years-long journey required to reach it. Several missions to Enceladus have been proposed, all facing the same fundamental challenge. Getting there takes about as long as getting to Saturn, 6 to 7 years or more. Uranus and Neptune, the ice giants, have received far less attention than the gas giants closer to the Sun. The long journey times to these distant worlds, coupled with the infrequency of favorable launch windows, have meant that only Voyager 2 has visited them. However, the scientific community has expressed strong interest in returning to these planets. A mission to Uranus has been identified as a high priority in planetary science, with potential launch dates in the 2030s. The journey time would be substantial, likely 12 to 15 years, even with gravity assists, meaning that scientists and engineers working on the mission might not see the results until they're near retirement. This multi-generational aspect of outer solar system exploration, where missions span decades from conception to completion, represents a unique challenge in maintaining institutional knowledge and public support. Neptune's moon Triton is thought to be similar to Pluto in composition, a captured Kuiper Belt object that was gravitationally snared by Neptune. Triton has a thin atmosphere and possible cryovolcanoes that erupt nitrogen instead of molten rock. Voyager 2's brief flyby in 1989 revealed a fascinating world, but we've learned little more in the decades since. A mission to Neptune and Triton would take 12 to 15 years or possibly longer, depending on the trajectory and whether gravity assists are used. The long journey time makes such a mission a major commitment, likely costing billions of dollars and requiring support across multiple administrations and budget cycles. The relationship between journey time and mission cost is complex but significant. Longer missions require spacecraft that can function reliably for extended periods, which generally means more robust and expensive systems. The operations team must be maintained throughout the cruise phase, even though little is happening beyond trajectory corrections and systems checks. Longer journeys mean longer waits for results, which can make it harder to maintain public support for space exploration. On the other hand, waiting for ideal launch windows and using slower but more fuel-efficient trajectories can reduce the mass that must be launched, potentially lowering costs. Mission planners must balance these competing factors, and different missions reach different conclusions based on their specific goals and constraints. The Kuiper Belt, the region beyond Neptune containing Pluto and thousands of other icy bodies, represents the frontier of what we've explored with spacecraft. New Horizons, after its Pluto flyby, continued into the Kuiper Belt and performed a flyby of the object Arrokoth in 2019. This encounter occurred 13.5 years after launch and at a distance of about 6.5 billion kilometers from the Sun.
New Horizons is still functioning and continues to study the space environment in the outer solar system, though it will eventually run out of power as its nuclear battery decays. The spacecraft is traveling at about 14 kilometers per second relative to the Sun, and it will take thousands of years to reach the inner edge of the Oort cloud. Several more ambitious missions to the Kuiper Belt have been proposed. An orbiter mission to a Kuiper Belt object would face extraordinary challenges. Not only would the journey take 15 to 20 years or more, but the spacecraft would need to slow down enough to enter orbit around the body with very weak gravity. This would require carrying substantial fuel, making the spacecraft very heavy, or using some advanced propulsion system. The scientific rewards would be great, allowing detailed study of a pristine remnant from the solar system's formation. But the long timeline and high cost have kept such missions in the proposal stage. The concept of a sun diver trajectory offers an intriguing possibility for reaching extreme distances relatively quickly. A spacecraft could plunge toward the sun, using the sun's immense gravity to accelerate to very high speeds, then shoot out into the outer solar system. The Oberth effect, named after Hermann Oberth, explains why this works. A rocket burn performed deep in a gravity well is more efficient than the same burn in free space. A spacecraft diving close to the sun could achieve speeds significantly higher than conventional trajectories allow, potentially reaching the outer solar system faster or traveling to greater distances. However, the extreme heat and radiation close to the sun pose severe engineering challenges, and the trajectory must be calculated with extraordinary precision to achieve the desired outcome. Solar system exploration isn't limited to destinations we've discussed. Comets, which originate either from the Kuiper Belt or the Oort cloud, follow highly eccentric orbits that bring them close to the sun periodically. Several missions have visited comets, and the journey times vary depending on the specific comet targeted. The Rosetta mission, which orbited comet 67P Churyumov-Gerasimenko and deployed the Philae lander, took 10 years to reach its target, using gravity assist from Earth and Mars. Comets offer unique scientific opportunities because they're relatively pristine samples of the early solar system, but their distant origins mean that intercepting them often requires long journey times. The interstellar medium, the space between star systems, begins at the edge of the heliosphere. Voyager 1 and 2 have both entered this region and are sending back data about conditions there. The transition from the solar wind-dominated heliosphere to the interstellar medium isn't sharp, but gradual, and studying this boundary region provides insights into how our solar system interacts with the galaxy. The journey to interstellar space takes decades even for our fastest spacecraft, and the Voyagers will continue traveling through this region until their power supplies finally fail, probably sometime in the 2020s. After that, they'll become silent ambassadors from Earth, carrying golden records with sounds and images from our world, traveling through the galaxy for millions of years. Breakthrough propulsion concepts continue to be researched, each promising to revolutionize space travel if the technical challenges can be overcome. The Variable Specific Impulse Magnetoplasma rocket, or VASIMIR, uses radio waves to heat plasma to extreme temperatures and then uses magnetic fields to direct it out the back of the spacecraft. VASIMIR could potentially achieve much higher exhaust velocities than chemical rockets, though it requires substantial electrical power. A VASIMIR-powered spacecraft with a nuclear reactor could potentially reduce Mars journey times to as little as 39 days in some optimistic projections, though many technical challenges remain to be solved before such a system could be built. The IM drive and other reactionless drives have been proposed, claiming to produce thrust without expelling propellant, apparently violating conservation of momentum. Most scientists are skeptical of these claims, and repeated tests have failed to conclusively demonstrate that these devices work as they claim. Small measured forces might be experimental artifacts or errors rather than real thrust. If such devices did work, they would indeed revolutionize space travel, but extraordinary claims require extraordinary evidence, and the evidence so far is insufficient. Space agencies continue to investigate these concepts at low funding levels, but they're not betting on them for future missions.
Laser propulsion represents another exotic concept. A powerful laser or array of lasers, either on Earth or in orbit, would beam energy to a spacecraft, either heating propellant that the spacecraft carries or pushing against a light sail attached to the spacecraft. The advantage is that the energy source stays behind, so the spacecraft doesn't need to carry heavy power generation equipment or fuel. The disadvantage is the enormous infrastructure required.
Laser systems powerful enough to accelerate spacecraft would need to be megawatt or gigawatt class, far beyond anything currently deployed for space applications. If such a system could be built, it might enable rapid transit through the inner solar system, potentially reducing Mars' journey times to weeks. But the technical and economic challenges are formidable. Magnetic sails, or mag sails, have been proposed as a way to use the solar wind for propulsion. While solar sails use the pressure of sunlight, mag sails would use the stream of charged particles flowing from the sun. A large superconducting coil would generate a magnetic field that extends for kilometers, deflecting the solar wind and producing thrust. Unlike solar sails, which become less effective farther from the sun, mag sails could potentially work throughout the solar system and even into interstellar space, where the interstellar medium would provide particles to push against. However, building and maintaining superconducting coils of the required size in space presents major technical challenges, and mag sails remain theoretical. The future of space propulsion will likely involve multiple technologies, each optimized for different types of missions. Chemical rockets will probably remain the standard for launching from Earth's surface and for landing on other bodies, where high thrust is needed. Electric propulsion systems, powered by solar panels in the inner solar system and by nuclear reactors in the outer solar system, will likely become the standard for moving between worlds, offering efficiency at the cost of low thrust. For human missions where journey time matters greatly, nuclear thermal or nuclear electric propulsion might become the preferred choice, offering a middle ground between the high thrust of chemical rockets and the high efficiency of electric drives. As we look further into the future, we might see the development of infrastructure that changes the calculus of space travel. Fuel depots in orbit around Earth, the Moon, and Mars would allow spacecraft to refuel, enabling them to use more fuel-intensive but faster trajectories. Manufacturing facilities in space could build spacecraft components that are too large or fragile to launch from Earth. Solar power stations could beam energy to spacecraft, allowing electric propulsion systems to operate at higher power levels than their solar panels alone could provide. Such infrastructure would be expensive to establish, but could dramatically reduce the cost and increase the speed of subsequent missions. The psychological impact of knowing that help is months away colors every aspect of mission planning for long-duration spaceflight. On Earth, even in remote locations, rescue is typically possible within hours or at most days. On the International Space Station, a Soyuz capsule is always docked, capable of bringing the crew home in a few hours if necessary. On a journey to Mars, if something goes catastrophically wrong, there is no rescue possible. The crew must solve any problems themselves with whatever resources they have aboard. This reality demands extreme reliability in every system, extensive redundancy in critical systems, and crews trained to handle any conceivable emergency. The long journey time means that even a small problem can become a crisis if it can't be repaired. The development of closed-loop life support systems becomes essential for long missions. Currently, the International Space Station recycles about 90% of water, but still requires regular resupply missions from Earth. For a mission to Mars or beyond, nearly perfect recycling is needed, or the mass of consumables becomes prohibitive. Oxygen must be extracted from carbon dioxide exhaled by the crew. Water must be purified and reused with minimal loss. Even solid waste might need to be processed to recover useful materials. The longer the journey, the more critical these systems become. Reducing journey time reduces the burden on life support systems and increases the safety margin if these systems partially fail. Artificial intelligence and automation will play increasing roles in long-duration missions. With communication delays of many minutes or hours, spacecraft must be able to operate autonomously for extended periods. AI systems can monitor spacecraft health, identify problems, and in some cases take corrective actions without waiting for instructions from Earth. For robotic missions, this autonomy is essential. The spacecraft must be able to respond to unexpected situations, whether scientific opportunities or technical problems, on its own. For human missions, AI assistants could help the crew by managing routine tasks, monitoring systems, and providing decision support. However, humans must remain in ultimate control, especially for critical decisions that affect crew safety. The question of how long it takes to reach each planet is intimately connected to the question of why we're going. A flyby mission, which passes close to a planet but doesn't slow down, can be faster than an orbital mission, which must shed velocity to be captured by the planet's gravity. A lander mission must slow down even more. The purpose of the mission shapes the trajectory and therefore the journey time. Scientists planning a mission must balance their desire for comprehensive data against the constraints of budget, technology, and patience. Sometimes a faster flyby mission is chosen over a slower orbital mission because the flyby can be accomplished sooner and at a lower cost, even though it gathers less data. The role of international cooperation in space exploration cannot be understated, especially for expensive missions to the outer solar system. The Cassini-Huygens mission was a collaboration between NASA, the European Space Agency, and the Italian Space Agency. The Mars Express and ExoMars missions involve ESA and Russia's Roscosmos. The International Space Station represents partnership among 5 space agencies. By sharing costs and expertise, space agencies can accomplish missions that would be difficult or impossible for any single nation. However, international cooperation adds complexity to mission planning and operations. The commercial space industry is beginning to play a role in interplanetary exploration, though so far primarily for Earth orbit activities and lunar missions. As launch costs decrease due to reusable rockets and increased competition, more missions to the planets might become economically feasible. Private companies might pursue asteroid mining, space tourism destinations beyond Earth orbit, or scientific missions funded by wealthy individuals or foundations. The journey times to various destinations won't change unless new propulsion technologies are developed, but the frequency of missions might increase if costs come down sufficiently. A more robust space economy could develop, with regular cargo flights to Mars during each launch window and scientific missions to multiple destinations happening concurrently. Education and public engagement are crucial for maintaining support for space exploration programs that take decades to complete. When a mission to the outer planets requires 10 or 15 years from launch to arrival, the public that supported the mission at launch might have moved on to other concerns by the time results arrive. Space agencies work to maintain interest through educational programs, public outreach, and sharing images and discoveries as they happen. The long journey times mean that space exploration operates on timescales longer than election cycles, longer than most careers, sometimes spanning a generation. Maintaining continuity of purpose across these timescales requires institutional commitment and public support that transcends budget pressures. The data returned from missions to distant planets takes time to analyze and understand. When New Horizons flew past Pluto in July 2015, it couldn't transmit all its data back to Earth immediately due to the low bandwidth at that enormous distance. The complete data set took 16 months to download. Scientists then spent years analyzing the data, publishing new discoveries and insights that continued long after the flyby itself. The scientific return from a mission extends years beyond the encounter, and in some cases decades, as researchers continue to extract new understanding from the data. This extended scientific productivity helps justify the long journey times and years of waiting. The human experience of space and time changes during long spaceflight. Astronauts on the International Space Station report that the normal markers of time on Earth become less meaningful. Days are divided into orbits, each 90 minutes long, with 16 sunrises and sunsets every 24 hours. Weeks and months blur together. On a journey to Mars, even this structure would be different. The sun would be visible constantly, though, getting smaller as the spacecraft travels further away. Earth would shrink from a disk to a point of light. Mars would grow from a point to a visible disk, and eventually a world filling the view. The psychological adaptation to this environment is something we're still learning about, and journey time affects this adaptation. Shorter journeys might mean less time to adapt, but also less time to suffer from isolation and confinement.
Sleep and circadian rhythms present challenges during spaceflight. The human body evolved to follow a 24-hour cycle driven by the sun, but in space, this natural rhythm can be disrupted. The International Space Station follows a 24-hour schedule to maintain crew circadian rhythms, but it's an artificial construct. On a journey to Mars, maintaining normal sleep-wake cycles would be important for crew health and performance, requiring careful attention to lighting, schedules, and possibly medication. The long journey means months of managing these biological rhythms in an unnatural environment, adding to the psychological burden of the mission. Nutrition during long spaceflight involves trade-offs between freshness, variety, nutrition, and storage life. Freeze-dried and thermostabilized foods can last for years, but they don't provide the psychological comfort of fresh food. Growing some fresh food in space is possible, and experiments on the International Space Station have successfully grown lettuce, radishes, and other crops. For a mission to Mars, supplementing stored food with fresh produce could improve crew morale and provide psychological benefits beyond the nutritional value. However, growing food requires space, water, and attention, resources that compete with other mission needs. The long journey time makes food quality and variety more important. Crews could tolerate monotonous food for a few weeks, but months of the same meals would be demoralizing. Exercise becomes essential during long spaceflight to maintain muscle mass and bone density. Astronauts on the International Space Station exercise about 2 hours per day, using specially designed equipment. On a journey to Mars, similar exercise regimens would be necessary, perhaps even more intense since the journey is longer. However, this exercise takes time away from other activities, whether scientific work, mission operations, or personal time. The spacecraft must include exercise equipment and space to use it, adding to the mass that must be launched from Earth. Shorter journey times would reduce the cumulative bone and muscle loss, potentially allowing astronauts to arrive at Mars in better physical condition. The question of what astronauts would do during the long months of travel to Mars or beyond is worth considering. Scientific observations could be made during the cruise phase, studying cosmic rays, the solar wind, and the space environment. The spacecraft systems would need regular maintenance and monitoring. Exercise would consume several hours daily. Meals, personal hygiene, and sleep account for more time. Communication with Earth, though delayed, would provide some connection to home. However, there would still be substantial free time, raising questions about entertainment, hobbies, and productive activities to maintain mental health. Books, movies, and games would be brought along, though the limited storage capacity means selections would need to be made carefully. Some crew members might learn new skills, study science, or work on personal projects. The ability to stay productive and engaged during months of travel would be an important selection criterion for Mars crews. The view from a spacecraft during the journey would be both magnificent and monotonous. The stars would appear as steady points of light, not twinkling as they do from Earth, since there's no atmosphere to distort their light. The sun would be the brightest object by far, too bright to look at directly even from Mars's distance. Earth would be visible as a blue point of light for a while, eventually becoming lost among the other stars. Mars would grow gradually brighter and eventually resolve into a disk with features discernible. The other planets might be visible depending on their positions. The view would change very slowly. The stars would maintain their positions, and the planets would shift only gradually. After the initial wonder wore off, the view might become familiar to the point of being unremarkable. Just as people who live near beautiful scenery often stop noticing it. The journey time means months of this view, spectacular yet unchanging. Landing on Mars after a 7-month journey presents its own challenges. The spacecraft approaches Mars traveling at several kilometers per second relative to the planet. Entry into the Martian atmosphere is violent, with aerodynamic heating raising the spacecraft's heat shield to extreme temperatures. Parachutes slow the descent, though Mars's thin atmosphere provides much less deceleration than Earth's atmosphere would. Retro rockets must fire in the final moments before touchdown. The entire sequence, from entry to atmosphere to landing, takes only minutes, a stark contrast to the months-long journey. The crew or robotic lander must survive this violent arrival after the long quiet cruise, and there's no second chance. Everything must work perfectly the first time. The exploration that follows landing makes the long journey worthwhile.
Whether robotic or human, missions to other planets answer fundamental questions about the solar system, the conditions necessary for life, and our place in the universe. The journey time, however, challenging, is the price we pay for access to these distant worlds. Each mission builds on previous ones, improving our understanding and our capabilities, gradually pushing the boundaries of what is possible. The months or years required to reach each destination test our patience and our technology, but they also demonstrate human determination and curiosity. The return journey from Mars or any other destination faces similar considerations as the outbound journey. The same orbital mechanics govern the trip home, and launch windows must be waited for. A spacecraft can't just turn around and come back. It must wait for the planets to align favorably. This means that human missions to Mars would spend considerable time on the surface, not just days or weeks, but over a year, waiting for the return window. The total mission duration, including both journeys and the surface day, would be approximately 2 to 3 years. This extended duration raises the stakes enormously compared to missions to the moon, where astronauts only were gone for about a week and a half at most during the Apollo program. The legacy of space exploration includes the missions that failed as well as the ones that succeeded. Not every spacecraft launched toward another planet has reached its destination. Some failed at launch, others en route, and some at arrival. The Soviet Union lost numerous Mars probes in the 1960s and 70s. NASA's Mars Climate Orbiter and Mars Polar Lander both failed in 1999. The European Space Agency's Beagle 2 lander reached Mars but failed to communicate after landing. These failures, while disappointing, contributed to our understanding and led to improvements in subsequent missions. The long journey times make failures particularly frustrating. Years of work and months of travel can end in moments if something goes wrong at arrival. The future of human exploration beyond Mars remains speculative but fascinating to consider. If breakthrough propulsion technologies are developed, missions to the outer planets might become feasible with any human lifetime. Even with journey times measured in years, humans might eventually explore the moons of Jupiter, Saturn, walk on Titan's surface, or dive beneath Europa's ice to explore its ocean. These missions would require entirely new levels of technology and commitment, but they're not physically impossible, just extraordinarily difficult and expensive with current capabilities. Each mission to Mars or elsewhere teaches us more about how to live and work in space, gradually building the knowledge and infrastructure that might eventually enable these more ambitious endeavors. The search for life beyond Earth motivates many planetary missions. Mars might harbor microbial life underground where liquid water could exist. Europa, Enceladus, and Titan are all considered potential habitats for life. Finding even simple life elsewhere in the solar system would be one of the most significant discoveries in human history, answering the old-age question of whether we're alone in the universe. The long journey times to reach these worlds are obstacles, but they're obstacles we're willing to overcome because the potential rewards are so great. Every mission that reaches another world expands the places we've searched for life, and even negative results are valuable, helping us understand what conditions are necessary for life to arise and survive. The economics of space exploration involve calculations that extend far beyond the immediate cost of building and launching spacecraft. When a mission takes 7 years to reach its destination, the team of scientists and engineers who designed it must be maintained throughout that journey. Mission control operations, tracking stations, and data analysis capabilities must remain funded. Missions that span decades from conception through planning, construction, launch, cruise, and operations require sustained commitment from funding. This long-term investment is difficult to maintain, yet it's essential for exploring distant worlds. The concept of mission resilience becomes paramount for long-duration journeys. A spacecraft traveling to Saturn for 7 years must be designed to function reliably throughout that period without maintenance or repair, at least for robotic missions. Every component must either last the entire mission or have redundant backups. Software must be robust enough to handle unexpected situations, yet flexible enough to be updated via radio commands from Earth if problems arise. The farther the spacecraft travels, the more challenging communication becomes, not just because of the time delay, but because the signal strength decreases with the square of the distance. By the time a spacecraft reaches Neptune, radio signals from Earth are extraordinarily faint, and the spacecraft's transmitter must be powerful enough for its signals to be detected across billions of kilometers. The thermal environment during the journey varies dramatically depending on the destination. In the inner solar system, spacecraft must dissipate excess heat from solar radiation. Venus missions require particularly robust thermal protection because of both the intense sunlight and the planet's own heat. In the outer solar system, the challenge reverses. Spacecrafts must retain heat and protect sensitive components from the extreme cold. At Jupiter's distance, temperatures in shadowed areas can drop to -200 degrees Celsius. At Neptune, it's even colder. Keeping instruments and systems at operational temperatures require heaters powered by the spacecraft's limited energy supply, another factor that affects mission design and capability.
The journey through different regions of the solar system exposes spacecraft to varying radiation environments. Near Earth, our planet's magnetosphere provides some protection. The asteroid belt was once thought to be highly radioactive, but proved relatively benign. Jupiter, however, is surrounded by intense radiation belts that rival the worst environments anywhere in the solar system. The Galileo spacecraft accumulated so much radiation damage during its years orbiting Jupiter that its electronics degraded noticeably. Europa orbits within Jupiter's radiation belts, making missions to that moon particularly challenging. Any spacecraft or future astronauts would need extensive radiation shielding. The journey time affects the cumulative radiation exposure, but the destination's radiation environment often matters more for mission planning. Historical missions have demonstrated both the possibilities and limitations of interplanetary travel with chemical propulsion. The Mariner missions of the 1960s pioneered flyby trajectories to Venus and Mars. The Viking landers in the 1970s proved that we could land on Mars and operate there for years. The Voyager missions showed that the outer solar system was accessible and that spacecraft could function for decades in deep space. Galileo demonstrated that we could orbit Jupiter despite the harsh radiation environment. Cassini revealed Saturn's system in exquisite detail over 13 years of operations. Each mission pushed boundaries and established new benchmarks for what's achievable. More recent missions continue this tradition of exploration. The Mars Science Laboratory mission, which delivered the Curiosity rover to Mars in 2012, took the 7-month journey we've discussed extensively. The spacecraft that carried Curiosity used a novel landing system called the Sky Crane, where a rocket-powered platform lowered the rover to the surface on cables, then flew away to crash at a safe distance. This system proved so successful that it was used again for the Perseverance rover in 2021. These missions demonstrate that even with journey times that haven't changed fundamentally in decades, our capabilities at the destination continued to improve. Rovers now carry more sophisticated instruments, can travel farther, and can operate for longer periods. The Juno mission to Jupiter, which arrived in 2016 after a 5-year journey, uses a highly elliptical orbit that takes it close to Jupiter's poles and then far out, minimizing time spent in the most intense radiation. This orbit was chosen specifically to extend the spacecraft's lifetime despite Jupiter's harsh environment. The journey time to Jupiter couldn't be reduced without different propulsion technology, but the mission profile was carefully designed to maximize scientific return once there. Such considerations shape every aspect of mission planning. Journey time is just one factor among many that must be optimized. The Parker Solar Probe, launched in 2018, follows a trajectory that will eventually take it to within 6 million kilometers of the Sun's surface, closer than any previous spacecraft. To achieve this, it uses multiple gravity assists from Venus, with each pass dropping its perihelion lower. The mission will take 7 years to reach its closest approach, not because the Sun is far away, but because achieving the right trajectory requires this careful choreography. This mission illustrates that journey time isn't always about distance. Sometimes it's about achieving precisely the right orbit or trajectory, which can take years even when the destination is relatively close. The ExoMars Trace Gas Orbiter, a joint mission between the European Space Agency and Roscosmos, took 7 months to reach Mars after its 2016 launch. It carries instruments designed to search for trace gases in Mars' atmosphere, particularly methane, which could potentially be a sign of biological activity. The journey time matched previous Mars missions because it followed a similar Hohmann transfer trajectory. The mission demonstrates international cooperation and also shows how standardized certain aspects of interplanetary travel have become. We know how to get to Mars, and the journey time is well established even if the scientific objectives of each mission differ.
The Bepi-Colombo mission to Mercury, a collaboration between ESA and the Japan Aerospace Agency, launched in 2018 and will reach Mercury in 2025, after a 7-year journey. As discussed earlier, reaching Mercury is challenging despite its relative proximity because of the need to shed orbital velocity. Bepi-Colombo will use 1 flyby of Earth, 2 of Venus, and 6 of Mercury itself to gradually slow down enough to enter orbit. The trajectory is a masterpiece of orbital mechanics, carefully calculated to achieve the desired result with minimal fuel expenditure. The long journey time is the price paid for making the mission feasible with current rockets and spacecraft. Looking at this catalog of missions, past and present, reveals patterns in journey times that reflect fundamental physics. Mars missions typically take 6 to 9 months. Venus missions take 3 to 5 months. Mercury missions require complex trajectories taking several years. Jupiter missions take 5 to 6 years unless they're flyby missions like New Horizons that can go faster. Saturn missions take 6 to 7 years. Uranus and Neptune missions take over a decade. These timescales aren't arbitrary, they emerge from the orbital mechanics of the solar system and the capabilities of our chemical rockets. Future missions using advanced propulsion could change these timescales, but with current technology, they remain remarkably consistent. The concept of in situ resource utilization could affect return journey times for future human missions. If astronauts could manufacture rocket fuel on Mars using local resources, particularly water ice and atmospheric carbon dioxide, they wouldn't need to carry return fuel from Earth. This would dramatically reduce the mass that must be launched from Earth, potentially allowing for larger habitats, more supplies, or more crew members. The return journey time would still be governed by orbital mechanics, still taking 6 to 9 months, but the mission would be more feasible. Similar concepts could apply to the Moon, asteroids, or even the moons of other planets, though the technical challenges increase with distance from Earth. The development of space nuclear reactors could enable new mission profiles. Current radioisotope thermoelectric generators produce hundreds of watts of electrical power, sufficient for science instruments and communications, but not for high-power propulsion systems. Fission reactors, capable of producing kilowatts or megawatts, would enable electric propulsion systems with much higher thrust, potentially reducing journey times throughout the solar system. NASA and other space agencies are developing small nuclear reactors for space applications, though none have flown yet. When this technology matures, it could represent a significant advancement in our ability to explore the solar system efficiently. The role of small satellites and CubeSats in planetary exploration is growing. These miniature spacecraft, some weighing just a few kilograms, can be built more quickly and cheaply than traditional large probes. Several CubeSats accompanied NASA's InSight Mars lander in 2018, successfully relaying data during the landing. Future missions might deploy swarms of small satellites to provide multiple observation points or redundancy. For these small spacecraft, journey times are the same as for larger probes, sharing the same trajectory, but their lower cost might enable more frequent missions and more risk-taking in mission design.
Additive manufacturing, commonly known as 3D printing, could eventually allow spacecraft to manufacture spare parts during the journey or at the destination. This capability would reduce the need to carry every possible spare part from Earth, potentially reducing mass and increasing mission reliability. For a journey lasting months or years, the ability to print a replacement component when something fails could mean the difference between mission success and failure. The technology is still developing, but experiments on the International Space Station have demonstrated that 3D printing works in microgravity. The question of planetary protection becomes more complex for longer missions. International agreements require that spacecraft sent to planets where life might exist must be carefully sterilized to avoid contaminating those worlds with Earth microbes. The longer a mission takes, and the more complex the spacecraft, the harder it is to ensure complete sterilization. Some microbes can survive for years in the harsh environment of space, protected within the spacecraft structure. For missions to potentially habitable environments like Europa's ocean or Enceladus's water jets, planetary protection requirements are especially stringent. These requirements can affect mission design, adding complexity and potentially mass to the spacecraft. Spantel-Remmer missions face the reverse challenge, preventing potential alien organisms from contaminating Earth. While the risk is considered extremely low, the consequences could be catastrophic if harmful organisms were inadvertently brought to Earth.
samples returned from Mars or other potentially habitable environments must be contained and studied in secure facilities until they're proven safe. This requirement adds complexity to sample return missions and extends the time between sample collection and scientific analysis. The Mars Sample Return mission, currently in planning, will include multiple layers of containment to ensure that any Martian material remains isolated until it can be properly studied. Climate and weather on other planets affect landing opportunities and can influence mission timing. Mars experiences global dust storms that can last for months, reducing sunlight and threatening solar-powered equipment. Mission planners try to avoid landing during dust storm season when possible, though the storms can be unpredictable. Titan's weather includes methane rain and possibly seasonal changes in cloud cover. Jupiter's atmospheric dynamics create storms that persist for decades or longer. Understanding these conditions and planning around them requires long-term observations from previous missions and adds another layer of complexity to mission planning beyond just the journey time. The motivations for space exploration vary among different stakeholders. Scientists seek to understand the solar system's formation, evolution, and potential for life. Engineers aim to develop new technologies and overcome challenging problems. The public often responds to the sense of wonder and adventure that space exploration provides. These different motivations can align or conflict, affecting which missions receive funding and support. Long journey times test all these motivations. Scientists must wait years for data, engineers must design systems that work reliably for extended periods, and the public must sustain interest despite long waits between dramatic events. Education and inspiration represent important but difficult to quantify benefits of space exploration. Images from Mars rovers, Saturn's rings from Cassini, and Pluto's surface from New Horizons inspire students to pursue careers in science and engineering. The challenges of space exploration drive innovation in materials, computers, robotics, and many other fields. Technologies developed for space often find applications on Earth. The long journey times actually contribute to this educational value. Students can follow a mission from launch through cruise to arrival and beyond, seeing the entire arc of a scientific endeavor and understanding that important discoveries require patience and persistence. The philosophical implications of exploring other worlds are profound. Finding life elsewhere in the solar system would answer one of humanity's oldest questions and would fundamentally change our understanding of our place in the universe. Even if we find that we're alone in the solar system, that knowledge is valuable, helping us understand how rare or common life might be in the cosmos. The time required to reach distant worlds and search for life tests our commitment to answering these fundamental questions. Are we willing to invest years or decades to find answers that might not arrive in our lifetimes? The history of planetary exploration suggests that we are, that our curiosity drives us to explore despite the long timescales involved. The future trajectory of space exploration will likely include both continuity and change. Chemical rockets will probably remain the standard for Earth launch for decades, though reusability will make access to space cheaper. Electric propulsion will become more common for interplanetary transfers, especially for cargo missions where journey time is less critical. Nuclear systems, whether thermal or electric, might enable faster human missions to Mars and perhaps to destinations beyond. More exotic technologies remain in the research phase, but could eventually revolutionize space travel. Throughout all this evolution, the fundamental challenge remains. The solar system is vast, and traversing it takes time. The international space community continues planning future missions despite budgetary constraints and competing priorities. Missions to return samples from Mars, orbit and land on Europa, explore Titan with a flying lander, and return to Uranus and Neptune are all under consideration or active development. Each mission requires years of planning before launch, then months or years of travel before arrival, then potentially years of operations at the destination. The scientists and engineers working on these missions often dedicate significant portions of their careers to single missions, a testament to their commitment and passion for exploration. Private space companies are beginning to look beyond Earth orbit. SpaceX has announced plans for Mars missions, while other companies consider asteroid mining or lunar bases. The involvement of private enterprise could accelerate the pace of space exploration if commercially viable activities can be established. However, the fundamental physics of orbital mechanics won't change for private companies more than for government agencies. Journey times will remain governed by the same laws, though perhaps new technologies or more aggressive mission profiles could push the boundaries of what's possible. The concept of a multi-generational mission to the stars captures the imagination, though it remains firmly in the realm of science fiction. Even with advanced propulsion, journeys to other star systems would take decades, centuries, or longer. Such missions would require spacecraft large enough to support entire communities, with closed-loop life support, food production, and social structures capable of sustaining themselves for generations. The journey times we've discussed for interplanetary missions, measured in months or years, seem trivial by comparison. Yet interplanetary missions are the necessary precursor to any eventual interstellar capability. We must learn to live and work in space for extended periods within our own solar system before we could possibly venture to the stars. The ethical dimensions of space exploration include questions about how we treat other worlds. Should pristine environments like Europa's ocean remain untouched, or do the potential scientific benefits of exploration justify the risks? These questions don't have easy answers, and they become more acute as we develop the capability to send missions to more locations. The long journey times actually provide time for debate and consideration. By the time a mission reaches a distant world, years have passed during which scientists, ethicists, and the public can discuss the appropriate approach to exploration. The economics of asteroid mining depend critically on journey times and mission costs. An asteroid rich in platinum or other valuable metals would only be worth mining if the cost of extraction and return is less than the value of the materials recovered. Shorter journey times mean faster return on investment and lower financing costs. However, the journey time is just one factor. Launch costs, mining technology, and market prices for the materials all affect viability. Some analyses suggest that water mining for rocket fuel production might be economically viable before metal mining, because water can be used in space for propulsion, reducing the need to transport fuel from Earth. The concept of a space-based economy, where industrial activities occur in space rather than just serving Earth-based needs, requires infrastructure that doesn't yet exist. Manufacturing facilities, power stations, transportation networks, and habitats would need to be established. Journey times between different facilities would need to be reasonable for workers and cargo. The Moon and near-Earth asteroids might form the foundation of such an economy, because they're relatively close, with journey times of days or weeks. Mars could potentially be integrated into this economy despite the months-long journey times if sufficient value is generated there. The outer solar system would likely remain separate unless revolutionary propulsion technologies are developed. The health effects of long-duration spaceflight continue to be studied aboard the International Space Station. Twin studies, where one twin spends a year in space while the other remains on Earth, have revealed changes in gene expression, cognitive performance, and other factors. Some changes reverse upon return to Earth, while others persist. Understanding these effects is crucial for planning missions to Mars and beyond. If we discover that certain health effects are irreversible or cumulative beyond a threshold, it might impose limits on how long humans can safely travel through space, potentially limiting which destinations are accessible until better countermeasures are developed.
The selection of landing sites on other planets involves trade-offs between scientific interest and safety. The most interesting locations, such as steep-walled valleys or icy slopes, are often the most dangerous for landing. Flat, boulder-free areas are safer but potentially less interesting scientifically. After a months-long journey to reach another planet, mission planners must balance the desire to explore exciting terrain against the risk of losing the mission during landing. This calculation has evolved as landing technology has improved. The Mars Curiosity and Perseverance rovers were able to land in more challenging terrain than earlier missions could safely attempt. Communication architecture for deep space missions is evolving. Currently, most spacecraft communicate directly with Earth using large antennas on the spacecraft and on Earth. As more missions fly and traffic increases, this approach may become inadequate. Relay satellites around Mars already assist surface missions, and similar infrastructure might be established at other destinations. A relay system would allow landers and rovers to use smaller, less power-hungry radios, saving mass and energy. For the outer solar system, relay satellites could amplify signals from distant probes, potentially enabling missions that would otherwise be impossible due to power constraints. The concept of living off the land using resources found on other worlds extends beyond fuel production. Water can be split into hydrogen for fuel and oxygen for breathing. Regolith from the Moon or Mars could potentially be processed into building materials. Greenhouses could grow food using local soil supplemented with nutrients. Developing these capabilities would make long-duration missions and eventual settlements more feasible by reducing dependence on Earth supplies. The long journey times to Mars and beyond make resupply expensive and time-consuming, creating strong incentives to develop local resource utilization capabilities. The search for technosignatures, evidence of technology created by intelligent life, has mostly focused on radio signals from distant star systems. However, if intelligent life ever existed elsewhere in our solar system, there might be artifacts or other evidence remaining. The long journey times to distant worlds mean that any such search would take years or decades to complete thoroughly. So far, no evidence of past or present intelligence has been found anywhere in the solar system except Earth, but the search continues. Even ruling out the presence of past civilizations would be scientifically valuable, helping us understand the conditions necessary for intelligence to arise. The role of artificial intelligence in space exploration continues to expand. Current spacecraft have limited autonomy, following pre-programmed sequences and responding to specific conditions. Future AI systems might be capable of making more complex decisions, identifying interesting scientific targets, adapting to unexpected situations, and potentially even conducting experiments autonomously. For missions to the outer solar system, where communication delays make real-time control impossible, such autonomy would be extremely valuable. A spacecraft orbiting Europa could autonomously decide where to point its instruments based on what it observes, rather than waiting hours for commands from Earth. The impact of solar weather on interplanetary missions is an ongoing concern. Solar flares and coronal mass ejections can release bursts of radiation that damage spacecraft electronics and pose health risks to astronauts. The Sun follows an 11-year activity cycle, with some periods having many flares and others being relatively quiet. Mission planners consider the cycle when scheduling human missions, though the most dangerous events can occur at any time. A particularly severe solar storm during a journey to Mars could potentially deliver a lethal radiation dose to unshielded astronauts, making radiation monitoring and protection critical concerns. The development of spacesuits for use on other planets involves different requirements than suits designed for spacewalks near Earth. A Mars suit must allow astronauts to work effectively in one-third gravity while protecting them from the cold, low pressure, and dusty environment. The suit must be durable enough for repeated use over months, since a Mars mission wouldn't include the option to frequently return to Earth for repairs or replacements. Weight is still a concern, but less so than for lunar suits, because Mars's higher gravity makes heavy suits more manageable. The long journey time means that suits must be reliable and maintainable with the resources available on Mars. Throughout this extensive exploration of journey times to planets in our solar system, several themes emerge consistently. Distance matters, but it's not the only factor. Orbital mechanics, propulsion technology, mission objectives, and practical constraints all influence how long journeys take. Current chemical propulsion technology imposes certain limits: months to reach the inner planets, years to reach the outer planets, and decades to reach the edge of the solar system. These timescales haven't changed dramatically in decades, though our capabilities at the destinations have improved enormously. Future propulsion technologies promise to reduce these journey times, but they remain mostly in development,
requiring more research and investment before they can be enabled for faster missions. The human experience of these journey times adds another dimension. While robotic probes can hibernate during the cruise phase and function reliably for years or decades, humans require continuous life support, face health risks from prolonged exposure to microgravity and radiation, and must maintain psychological well-being during months of confinement. These factors make journey time particularly critical for human missions, creating strong motivation to develop faster propulsion systems or better methods of protecting astronauts during long journeys. The scale of the solar system becomes tangible when we consider these journey times in human terms. A 7-month journey to Mars means that astronauts would miss holidays, birthdays, and family events. They would watch their children grow up through delayed video messages. They would age noticeably during the mission. For journeys to the outer solar system, if humans ever venture there, these effects would be even more pronounced. A multi-year mission to Saturn would represent a significant fraction of a person's career and life, a commitment comparable to serving in a remote research station or on a long naval deployment, but more extreme in its isolation and danger.
The ultimate question isn't just how long it takes to reach each planet, but whether the journey is worth the time, cost, and risk. For robotic missions, the answer has consistently been yes. The scientific knowledge gained from exploring other worlds justifies the investment and patience required. For human missions, the calculation is more complex. Mars appears to be on the threshold of feasibility with current or near-future technology, which is why it receives so much attention. The outer planets remain distant goals, requiring breakthroughs before human exploration becomes practical. As we look to the future of space exploration, the journey times we've discussed will continue to shape what's possible and what missions are attempted. Engineers will continue working to develop faster, more efficient propulsion systems. Scientists will continue planning missions to exciting destinations throughout the solar system. And people around the world will continue looking up at the night sky, wondering about those distant worlds, and imagining what it would be like to visit them. The journey to reach those worlds takes months or years, testing our patience and our technology. But the rewards, the knowledge gained, the questions answered, and the sense of exploration and discovery make the long journeys worthwhile. Each mission that successfully reaches another planet demonstrates that the vast distances of the solar system, while formidable, are not insurmountable. We have the technology to reach every major planet, and we're developing the capabilities to explore even more distant and challenging destinations. The journey times may be long, but they represent achievable goals rather than impossible dreams. And that makes all the difference in turning our aspirations for space exploration into reality. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.